We spent a bunch of time deriving the general form of the heat equation, which is this equation that we had said related changes of temperature over time to changes of temperature over space, and then to other material properties and things that were relevant to the study of heat transfer. So now that we have the general form of the heat equation, the thing that we should try to do now is to try to see how we can take that perhaps a little intimidating general form, which is a partial differential equation, and then convert it into something that's a lot more, I guess, workable by applying simplifying assumptions that are relevant, that are valid for systems that we observe on our day-to-day lives. Okay? And so to get us started with that process, let me actually write down what the general form of the heat equation looks like. So it looks like this. The general form of the heat equation is a relationship between the thermal energy density, or the rate of change of the thermal energy density of a point in space with respect to time, and how that becomes connected to the divergence, which is that goofy kind of expression that's a function of rates of change of this heat flux vector, okay? Or more precisely, the negative of the heat flux vector, plus volumetric thermal energy generation rate at a point. So all of these quantities, you can imagine, are defined at a specific point. And so what we want to do is, right, we have partial derivatives with respect to time. We have partial derivatives with respect to space. Can we simplify this a little bit without losing the actual kind of physical or mathematical meaning of what's going on here? So what are some things that we could try to do? Well, here's one thing. One common assumption that is often applied when working with the heat equation is that the material properties of the object that we're considering are constant. And so what do we mean by that? Well, it just means that the specific heat capacity, the density, and the thermal conductivity, right, so Cp, rho, and K respectively, that these three things are not a function of time, that they're not a function of space, but that they're also not a function of like the temperature or the pressure or any other variable, any other factor that could show up in the analysis of this system. Okay, so we're just going to pretend like they're a single fixed number. And if we do that, then these material properties, Cp, rho, and K, can be extracted out from the derivatives in which they're encased in right now. So what does that look like? For this one, it's relatively simple, right? So if you use the chain rule and you notice that the rate of change of this and this with respect to time, right, of the material properties is 0, then what you wind up getting is just this. Simple enough, right? This is the rate of change of the temperature with respect to time multiplied by this combo of material properties. Over here, something that is equally simple, but perhaps a little bit funnier looking from the perspective of vector calculus happens. And it happens because if I take the K out, I'm left with the divergence of the gradient of a field, right, of the temperature. And what happens whenever we get this is that we refer to the divergence of the gradient of something using another vector calculus operation. So another like goofy little expression, which we will start to express in coordinates soon. And the expression that we wind up getting is called the Laplacian. Okay? And the notation for it is we just take the upside down triangle and we square it. And the idea behind the square is not that we're actually squaring anything, it's just that it's referring to the fact that this is supposed to be a second derivative. Like this thing is going to be a function of the second derivatives of the temperature field over space. Okay? So this is just the notation that people came up with. The 2 is there to tell you about the second derivativeness of it, and we'll see actual expressions for what this is when we actually start simplifying the equation further and further. Okay? So we wind up getting this if we assume that the material properties are constant. And then the Q dot just comes along for the ride. So this is the assumption that we get whenever we assume that material properties are constant. So what are some other assumptions that we could make that would simplify this equation as well? Another simplified form of the heat equation comes from a simple and common physical fact, or at least an approximately common, right? So the thing that we're going to talk about is always approximately true, but it's pretty well, like approximately true. I don't know how to phrase that correctly, but basically it's never exactly true, but it's almost always true. And that assumption is that there is no thermal energy generation inside of the material. So the general idea is that, like, if you take a piece of brick or any kind of material, usually you don't expect that material to be generating heat as a result of the conversion of some other mechanism of energy, right? So sure, if I take the brick and I rub it really hard against the wall, then mechanical energy via friction is going to generate some thermal energy. But if I just take a brick that's laying there and I mess around with it, I certainly wouldn't expect it to spontaneously start generating thermal energy. And so as a result, for inactive systems, it's commonly true that the Q dot is basically zero. Okay? And all that that does to the heat equation is it just, perhaps unsurprisingly, removes the Q dot. Okay? So this one's a simple one to talk about. So what are some other assumptions that we could make? Well, a common one, and one that we've been making over extended periods of time, at least from the perspective of these lectures, one assumption that we've been making over and over and over again is the assumption of steady state. And all that steady state says, all that steady state does, is that it indicates that nothing inside of the system changes over time. Okay, so not the K, not the CP, not the rho, not the Q dot, nothing in this system changes over time. And because nothing changes over time, this term necessarily has to be exactly equal to zero. Okay? And because of that, the equation winds up simplifying down to the following. And so this is kind of interesting, but perhaps not super surprising. Because what this is saying is that if we assume that the system is operating in steady state, specific heat capacities don't matter. Densities don't matter. The only material property that comes into play when trying to solve the heat equation, or this simplified form of it, is the thermal conductivity. The reason that I say that it shouldn't be surprising is because we never had to calculate the specific heat capacity or the density when we were trying to solve for the relevant variables inside of like certain systems where we had assumed steady state. Right? We never had to worry about what the specific heat capacity of the human body was. We were trying to figure out all of the relevant variables there because we assumed that the human body was operating at a constant temperature difference to the environment. Okay? And so as a result, the assumption of steady state not only simplifies the equation, but lowers the amount of different terms that show up. Right? You get rid of those two material properties entirely, and there's only one that ever shows up. So what is the other assumption, which is the final assumption that we are going to be covering? And the final assumption that we should consider is that heat transfer is going to happen in one dimension. Okay? So one-dimensional heat transfer. And the reason that we're going to assume this when we write down the heat equation is because it simplifies what is perhaps the most complicated term inside of the heat equation, which is this term right here, right? This double derivative, or this goofy expression of that's a function of second derivatives of the temperature field in space. And so what we really want to do is we want to come up with some assumption that allows us to simplify what this is to make, our lives a little bit easier. But this one-dimensional heat transfer assumption is still like pretty valid. Like it still applies to a lot of systems that we work with in our day-to-day. So like, for example, consider something we had seen before, the notion of a brick wall separating a room from an environment, right? Now, hypothetically speaking, there could be heat transfer in all kinds of different directions, right? There could be heat transfer upwards, there could be heat transfer this way. But really the only heat transfer that we care about, the thing that is going to dominate how energy moves around, is going to be the heat transfer that happens in this direction, or I guess this direction, right? Because of the fact that the thing that's causing a temperature imbalance, the temperature imbalance that we're trying to preserve, is the temperature imbalance between the room and the atmosphere. And so it makes sense to be able to kind of say, well, we have like a privileged direction in which heat transfer is occurring inside of this particular exercise. And so we're just going to assume that heat is only being transferred in that one direction, okay? And we've been implicitly kind of doing this for a bunch of different examples that we've worked on before. It's just now we can directly say it. And the way that this approximation affects this actually depends on the geometry in the coordinate system that you're using. Because think of the following, right? This is a perfectly valid scenario in which we can consider one-dimensional heat transfer, right? But we could also consider a situation where, like, let's suppose that I have some kind of like uranium rod, okay, that is like generating heat as part of some kind of uranium power plant or whatever. And this thing is surrounded by fluid, which can be water or air, whatever. Doesn't really matter. And you can imagine that this nuclear fuel rod inside of this nuclear power plant can get pretty hot. So it's going to be transferring a lot of that heat into the environment. Usually nuclear power plants, the point of the rod is that it gets hot, it boils the water that's around it, and then that water becomes steam, and then it powers a steam turbine or whatever. But anyways, the point is that this thing gets hot and then transfers thermal energy out into the environment. And so if it does that, is there one-dimensional heat transfer inside of this system? Well, maybe, maybe not. But one thing that we can approximate is we can just say, well, what if we just assume that all of the heat transfer in the system occurs radially outwards? Okay, so not necessarily in a single direction, but if we define like a radially outward direction, then at all points the heat transfer we can approximate is occurring, either this way or this way. And so this is still technically one-dimensional heat transfer, right? Because there's only one dimension, there's only one piece of information that will tell us how this can change, which is the distance from this central point to wherever it is that we're analyzing, okay? So if we assume that the heat transfer is happening in one dimension, it doesn't necessarily mean that we can't handle systems where, the direction in which the heat transfer is occurring changes in space. It's just that it can only depend on one thing, which is in this case r, right? It can only be a function of this r hat vector. So the reason that I spent a bunch of time talking about this is because of the fact that depending on what coordinate system I'm using, depending on which thing the heat transfer depends on, right? So like which coordinate system I use, this expression is going to change. It's actually going to show up differently. In a Cartesian coordinate system, so for the brick wall, we were talking about before, I can define an x hat direction, right? So Doesn't matter, it's just the x-hat direction. And we can take this thing over here and then turn it into the following simple expression. Well, simple-ish, which is just the rate of change with respect to x of k times the rate of change of t with respect to x. So whenever I'm dealing with a planar object, a planar one-dimensional heat transfer, whenever I'm dealing with that, this expression over here gets turned into this. Okay? And so you can see that, technically speaking, it's a double derivative. If I had also assumed that k was independent of x, right? If I had assumed that this material property was constant, then what I would have wound up observing is that I can actually simplify this further, and that I could write this down explicitly as k times the second derivative of the temperature with respect to x. Okay? Things get a little bit more complex once we start getting into other coordinate systems. And although we won't obviously go over all of them, let's talk about some of them. Here's another common one. So suppose that we're dealing with cylindrical coordinate systems, which might apply to the nuclear fuel rod that we were talking about before, right? So I'm really bad at drawing cylinders, so I apologize. But suppose that I have, a cylinder, and I want to construct a coordinate system such that the only direction in which heat transfer is occurring is outwards, okay? Radially outwards. And so if that's true, then this simplifies into something that's a little bit more complex than the expression that we had seen before, which is just 1 over r times the derivative with respect to r of k r times dt dr. So this turns into this. Okay? Now, if the k was just a random, if the material property of k, the thermal conductivity, was a constant, then I could just pull the k out, and then I wouldn't necessarily want to simplify it because I'm still going to get something a little strange because of that r that's in there. But nevertheless, you can imagine that by applying a lot of the assumptions that we've made before, in addition to the one-dimensional heat transfer assumption, we can eventually get stuff that's simpler than these derivatives. So this is what we get in cylindrical coordinates. The last case that I want to consider is what happens when we consider spherical coordinates. Okay? In spherical coordinates, in this case, now this is like a ball. This is a proper ball. I'm not even going to try to do the shading because I'm going to get it all wrong. But this is a sphere, and you can imagine that the outwards direction now is not privileged, right? So in the cylindrical case, like there was a radial outwards direction, but then there was also an axial direction. That didn't account for the fact that, I could move radially outwards from the center of the cylinder, but I can also move axially, right? So that r hat didn't account for that. And so I guess, in the interest of having different notation, I'll write it like this. We can come up with this other r hat vector that is really purely radially, a pure radial outward direction. It points radially outwards in 3 dimensions, not just 2, like in the cylindrical case. And for a spherical coordinate system, the way that we write down this expression is just 1 over r squared, that's the derivative of k r squared dt dr. Okay? So this is the expression that we get. It's very similar to what we got in the cylindrical case, except that now we've got this r squared that shows up, the 1 over r squared over here, and then the r squared over here. So that's what it is. Now, if I have a bunch of other goofy coordinate systems, if I have a bunch of other different geometries, then I can imagine that this term changes into different things, right? Things that we may not have seen. But for the moment, for planar, cylindrical, and spherical geometries, where we assume that the heat transfer is only happening either, in one planar direction or radially outwards, whatever that means from the cylindrical or spherical perspective, we know what the expressions will look like. And so now let's bring it all together. So what happens if I take all of the assumptions that I've just made and apply them together? Okay? Well, let's think about it. So the first assumption we made was that material properties were constant. Okay? So that just makes the heat equation turn into this. So that's assumption number one. Assumption number two that we had made was that there was no volumetric heat generation, which just gets rid of the Q. Then we make the assumption that, oh, well, what if we assume that the system is in steady state, right? The temperatures don't change over time. Well, if we do that, then this whole term over here, this whole thing goes to zero. And then what if we assume that the heat transfer that was occurring in the system was one-dimensional? And then that simplifies this goofy vector calculus expression into something that looks like it's partial derivatives, right? And because there is no dependence on anything else, right? Because time no longer shows up, those partial derivatives can be substituted with total derivatives. And so just to give you a quick example of what that would look like in a planar geometry, right? So if we assume some planar one-dimensional heat transfer in the x direction, this turns into the following very simple ordinary differential equation. And so all that we would have to do now in order to try to figure out what the temperature of this system was as a function of x, right, because it can't be a function of time, is to see how we can't solve this ordinary differential equation. And we will do that next time.